What if we could go backwards in time? Hello, my name is Brian Giffen. I'm an assistant professor at Oklahoma State University, and today I'm going to be sharing some work that I've been pursuing over the past year or several months, but it really only came together in the past couple weeks, during which time I presented at the U.S. National Conference for Computational Mechanics. The subject of my talk is on so-called bit-reversible computational methods and some of their uses in the context of solving large-scale optimization and inverse problems. So, a lot of interesting things to get into, a lot of fun things to dive into with respect to the mathematics and all that. But before we get into that subject, let's actually look at why we actually want to reverse the flow of time to begin with and how that's even useful to us. So, in general, when you're solving optimization or inverse problems, and a good example of this might be acoustic sensing or seismic imaging, where, for example, let's say you have some point source or excitation that you apply to some domain of interest, like some geological medium, for which you would like to determine what are the properties of that medium. Ahead of time, you don't really know what those properties are, but you might be able to excite that medium and record what its responses are on the surface or at some discrete sensor locations. And using that discrete sensor data, you can try to reverse or infer what those material properties are by constructing an equivalent model. You could think of it like a digital twin of sorts that represents that medium, which you attempt to tune in order to match the recordings that you received from those sensors. But to do that, you have to solve an optimization problem to find out what are the most likely properties that would lead to those recordings or outputs at those sensor locations. And to do that, you have to analyze your computational model by solving some transient dynamic forward problem, the elastodynamic wave equations. And then, once you've solved that problem forward in time, you have to figure out, how do I adjust the parameters of my model to better match my sensor data? And to do that, generally speaking, you need to solve an optimization problem. And there are many ways you can solve the optimization problems. You can solve it just by brute force, to guess and check a bunch of different variations of the soil properties at all the different locations of interest throughout this domain that you're examining. But for very large problems with very many parameters that you might have in some large domain like the Earth, it's just infeasible to exhaustively search that space spanned by that huge number of parameters. So the way that people work around this is by effectively using gradient-based optimization techniques. You figure out, how would the output of my simulation change if I perturbed the inputs, my parameters of interest, just a tiny amount? And to determine such a gradient, you need to compute the derivative of my outputs with respect to the inputs. This is sometimes called a sensitivity analysis, but if you're doing it in the context of a computational analysis, there are many ways that you can do this. And specifically for solving time-dependent problems, one common way of doing this is the so-called adjoint variable method. Effectively, it entails first solving the forward problem in time, and then solving some equivalent or adjoint problem associated with the forward problem that involves not solving a problem forward in time, but rather a corresponding problem posed backwards in time. And using those variables, then you can very easily and efficiently compute the gradients of this objective function that you're trying to optimize with respect to the input parameters of interest. In this case, maybe it's the soil properties at each individual location throughout the computational domain. So that's a very brief overview of some forms of optimization and inverse problems when solving them in a transient dynamic context using the adjoint variable method. And the adjoint variable method is a great method to use if you have a very large number of parameters that you're trying to optimize and you're solving a transient kind of or time-dependent or path-dependent optimization problem. However, some of the limitations of that method are that you have to solve this forward problem in time, and not only that, but you have to actually reconstruct that forward problem throughout the entire duration of the simulation in order to solve the adjoint problem going backwards in time. So the way that it works is that in order to determine how you propagate your adjoint variables backwards in time, you have to know what the forward solution state was at each preceding time state as you propagate that set of adjoint variables backwards in time. So to do that, you either need to store the entire forward solution at every single time state in the analysis as you step backwards in time. But to do that requires a lot of memory. You basically have to store the entire history of the simulation in memory. And if you take a lot of time steps, and if the problem is sufficiently large, then you may end up being memory bound in terms of your computations. So it's not always feasible to do that. So the workaround that people use is to instead do checkpointing. Effectively, you only save a discrete number of the forward solution states at selectively chosen points in time, from which you can step back to those checkpoints and then play the simulation forward in time to reconstruct the forward solution at some intermediate time states that you need in order to compute or update the adjoint problem going backwards in time. The whole concept of checkpointing is actually not so different from the movie Memento. And if you haven't seen the movie Memento, go and watch it. It's a great film, and it obviously has bearing in the present context. And to give you the basic premise of how the movie relates to this notion of checkpointing, effectively, the movie Memento plays backwards chronologically in time, but it does so by skipping back to some scene that occurred in the past chronologically, and then that scene plays forward in time up to the beginning of the last scene, which occurred sometime in the future. So you're continuously jumping backwards in time to these checkpoints and then playing the simulation or the movie forward in time. And that's kind of a fun idea, but the question is, if you're bound by these different constraints, either having to store the entire simulation in memory, which is very memory intensive, or if you're having to reconstruct the solution using this checkpointing scheme requiring more computations, either one of those two methods is going to require extra effort or extra memory. So the question is, can we do better? Is there a way of further minimizing our memory or computational requirements through some other technique that's not storing the entire solution and not checkpointing? And the answer comes from, let's make another analogy to yet another Christopher Nolan movie, posing a different question. What if we could just go backwards in time? Don't think about checkpointing or anything like that. What if I knew what the solution was at some time tn, and I just wanted to reconstruct this forward solution at some preceding time tn minus 1? If I had some forward in time update procedure, couldn't I just invert that relationship and come up with what the preceding solution was at the last time step? Is that even physically possible? Does that even make sense? It sounds like it defies the laws of physics, much like the movie Tenet, another Christopher Nolan movie which entails reversing the laws of physics and time flowing backwards. Now, admittedly, if you ask me, Memento is the better movie, but Tenet is really the greater technical feat. In any case, film analogies aside, really this is the central question of the talk today that I'll be presenting. Can you even go backwards in time? And if you can, what are the limitations? What are the challenges that we need to overcome to enable this? And how do we even make it work? So the main advantages of actually trying this, however, is that if we could just go backwards in time, then we wouldn't need to store the entire solution, states in memory because we can just reconstruct them going backwards. Certainly requiring some recomputation, but definitely requiring less recomputation than we would have to do if we were using some kind of checkpointing scheme. And better than that, if we don't even have to save any intermediate states in memory, and we don't have to do this recomputation approach in the case of checkpointing, then we actually, minimize our memory requirements, minimize our computational requirements, and potentially also minimize our memory bandwidth limitations, or basically get around the need for transferring memory between distinct pools that might have some latency associated with them. That's particularly advantageous if you're trying to accelerate these computations on a GPU system or something that has some limitations on how fast you can transfer old solution states to and from memory in order to do the checkpointing and recomputation stages. All right, so that's the idea. Now let's get into the details. So the question becomes, is this even possible? Can we even do this? And well, it turns out that for certain physics and certain systems, it is possible to actually reverse the flow of time, somewhat paradoxically. Now, if you think about some prototypical examples of this, one great example is just Newton's laws of motion. Or in other words, in the case of, let's say, solving some transient dynamic problem like we were looking at before, and with that soil property parameter estimation problem, that entails solving the elastodynamic wave equations. And that effectively is, solving some kind of transient dynamic problem. But that system is actually time reversible. If we wanted to, we could actually come up with some kind of transient dynamic time integrator that would allow us to go backwards in time just by basically flipping the sign of the time step we're taking in our computational analysis. And there are certain numerical time integrators, such as the leapfrog integrator, which are naturally time reversible and furthermore preserve the symplectic structure of those particular Hamiltonian systems. So the leapfrog time integrator, so named because it involves alternating the update between these velocity variables stored at the half step of a given time discretization, and the displacement variables stored at the whole step locations of that corresponding time discretization. And the really cool thing about this leapfrog integrator is that effectively it looks the same going forwards and backwards in time, and more than that, it's an explicit integrator going forward in time, just as it is an explicit integrator going backwards in time. So whatever computational effort required to solve the forward problem is basically the same computational effort we would need to expend if we were to reverse those steps and traverse the forward problem going backwards. So it's a great candidate to explore this whole concept with respect to. And, it's an easy one to test. We can just implement this really quickly and see, does it even work? Can we do this? And it turns out that we almost can. We can solve certain problems like this chaotic triple pendulum problem and traverse what is the trajectory of this triple pendulum going forwards in time. And then we can test what happens if we try to reverse that same simulation and go backwards in time. And the ideal situation is that not only should it work, that we should traverse going backwards, but we should ideally get exactly the same solution that we had going forwards in time. The problem is, as you can see from this animation, that we don't exactly recover the original solution that we got when we solved the forward in time problem. And why is that? You can see that traversing the blue path going forwards in time and then traversing this magenta path going backwards in time, it almost does it, but then it kind of falls off the rails. At a certain point, it just follows a completely different trajectory. Part of that has to do with the simple nature of this triple pendulum problem being a chaotic system. It's one that's very sensitive to inputs or very small errors that can perturb the solution and cause it to diverge from whatever trajectory it had to begin with. And essentially, this chaotic pendulum, being sensitive to those errors, really raises the question, well, is there some error that's being incurred that accounts for why it doesn't traverse that same trajectory going backwards in time? And the answer is yes. The source of that error actually turns out to be due to floating point arithmetic errors. And in particular, floating point errors or round-off errors due to addition and subtraction operations. During our forward update, we continually update our velocity and displacement variables by adding some kind of small adjustment or delta V and delta U as we go forwards. And when we go backwards, we perform the reverse operation, subtractions of those same quantities. Now, the problem is, if we're using floating point arithmetic, we incur some small error. And that error leads to precisely why we can't actually reverse this in time. So that's the problem. Somehow we need to get around this limitation that floating point arithmetic errors will inherently lead to potentially differing solutions when we try to reverse the flow of time. So what's the fix for this? Can we even resolve this issue? Well, it turns out we can. And the answer comes from not using floating point, but instead using fixed point algorithmic procedures and fixed point arithmetic. Now, what is fixed point anyways? And maybe you're familiar with it, maybe you've heard it before, but fixed point numbers are really no different from floating point numbers. The only difference is that we fix the radix point associated with those numbers. So in a computer, you represent a number using a mantissa, a radix, and an exponent if you're looking at a floating point number. A fixed point number is exactly the same thing, but you fix the radix point. So you have the same radix and the same exponent for the entire duration of the simulation, which basically means that you can represent such numbers in an isomorphic fashion to a set of integers with a fixed range. So in other words, I can represent these fixed point numbers simply as integers and then replace all of my floating point operations with equivalent integer arithmetic operations. Now, the disadvantage of using fixed point numbers is that now you're constrained to a fixed dynamic range. Or rather, it's not a dynamic range at all. You have a fixed range of numbers which you can represent using this so-called fixed point numeric representation. And that range is determined by the size of the integers that you're using to represent the mantissa, and also dependent on the choice for the radix point. So in the simple case where, let's say, you have some number where the radix that you've chosen is 10 to the minus 6 or something like that, then effectively, if you're using 32-bit integers to represent that number, then you can represent any number in between, let's say plus to minus 2000, and any number down to as small a magnitude as 1e to the minus 6. Now, in comparison, if I were to expand the range of numbers in my fixed point representation using 64-bit integers instead of 32-bit integers, I can substantially increase that range. So depending on the type of problem that I'm solving, I might have to be careful about what level of precision am I using. Is it 32-bit or 64-bit integers? And also, what radix am I choosing for representing these fixed point numbers? And in general, that'll be a problem-dependent thing that I have to set. I need to choose what is the reasonable range of numbers that I need to be able to represent in terms of my different solution variables, both for my displacements and my velocities. But it turns out that both of those two things, displacements and velocities, I can actually choose different radices to represent those different types of degrees of freedom, and that can be very advantageous. Okay, so here's the question. Does it work? Well, let's try again this this same triple pendulum problem and see what happens. It turns out that you do exactly reconstruct the original solution that you had going forwards in time if you use this fixed point arithmetic substitution. So using fixed point numbers to represent my displacement and velocity variables and carrying out all those additions and subtractions in a perfectly reversible way using integer arithmetic, I get a fully bit-reversible implementation of the leapfrog algorithm, simply by using fixed point arithmetic. And this is not a new concept. I'll point out that this has been around in various forms and applied to various different domains in physics, including as far back as applications to molecular dynamics. The original idea came from a paper by Levesque and Verlet and has been used in a variety of different contexts for continuum mechanics, n-body simulations, and also for chaotic dynamic systems. And I have to say, I can't claim credit for this particular instantiation with this triple pendulum problem. Actually, that credit goes to Stam of various fame in the computational domain applied to mostly visualization and animation. Stam is fairly notable in that particular community. And he also has some very nice interactive demos that you can play around with, including a demo exactly of this problem. So you can go online and check out the link and play around with that. Pretty fun stuff. Anyways, so this works. You can reverse the flow of time and reconstruct the original solution that you had. But what the heck? I mean, can this work for any type of physics? I mean, this really raises a lot of intriguing questions. Can you actually go backwards in time in general? And the answer is, well, not exactly. All of these problems and all of these applications that this idea has been applied to have been limited primarily to Hamiltonian systems, ones which are reversible in time and which also conserve their total energy. Now, that whole idea breaks down as soon as you introduce any kind of numerical or physical types of dissipation in your problem. For example, damping. Consider a slightly different problem. Suppose I had a block, I put it in this well, and I let the block slide to the bottom of the well, and over time it settles at this bottom of this well because I'm applying some kind of damping to this problem. Mass proportional damping in particular in this example. And that damping slows down the kinetic energy of my problem and causes the block to eventually settle at the bottom of this well. Now, you'll notice the total energy of the problem as you run it forwards in time diminishes as the block starts to settle down. However, when I reverse the flow of time, I don't get back to the original total energy of my system. And moreover, the block doesn't go back to its original position. So what the heck is going on? I'm using fixed point arithmetic in that whole concept that was applied in those different contexts, but I'm not getting back the original solution. Why is that? Why do I not recover the original solution? Well, it turns out the issue is my additions and subtractions, all of the, those arithmetic operations using fixed point arithmetic are perfectly reversible still. The only difference is by introducing damping, I actually involve a different additional step that entails multiplying or decrementing my velocities by some additional term. That's always some factor that's less than 1, basically. It means that as I continually apply this damping factor to my velocities, my velocity will slow down over time or get smaller and smaller. And because of that, as the velocity variables are continuously decremented, I actually find that the total system energy tends to 0, and in the process, I actually lose information. I lose information in representing the state of my system by applying this extra damping factor and through the multiplication operation itself. So, here's the observation. Even though additions and subtractions using fixed point arithmetic are perfectly reversible, multiplications and divisions are not reversible operations. And that's the central challenge. That's the problem that we need to overcome if we want to try to extend that same concept of bit reversibility to apply in the context of dissipative dynamic systems with damping or some other types of dissipation mechanisms going on. So that's the real problem. We have to figure out a way to come up with a reversible form of multiplication in the context of using these fixed point numbers. So what's the main problem with multiplications and divisions not being reversible when we're talking about fixed precision numbers? And forget about fixed precision numbers, think more about integers and the operations of integer multiplication and integer division. Integer multiplication is actually a perfectly reversible operation. Given some input variable x, if we scale that variable or multiply it by another integer, a, and then try to reverse that operation by dividing again by a, I'll get back the original value of x that I put in. However, division is not a reversible operation, and not just any old division, Euclidean division, or integer division, which is typical in most implementations of computing languages like C++ or Python or all the stuff that you're probably familiar with. Integer division involves dividing some integer x by another integer a, such that I also incur some remainder after division, r, which is nothing more than x modulo a. And when I try to take x divided by a, which excludes that remainder or kind of throws the remainder away, and then if I multiply again by a in an attempt to reverse the division operation, what I'll find is that I'll get back a different number that isn't the original value that I put in. It differs by this term x modulo a, the remainder term that we got rid of when we carried out this integer division operation. And that's the problem. Every time we do a division operation, we're losing information in the form of this remainder after the division. That information, effectively a bunch of bits in our simulation state that gets thrown away, is crucial information that we need if we want to reverse this operation and go backwards in time or backwards through the computations. So the real question is, can we preserve that information somehow? Rather than throwing away the remainder term when we carry out a division, is there a way of keeping track of those remainders such that we can then reverse these operations and reconstruct the original solution in a bit-for-bit exact sense? Well, it turns out that there is a way to do this, and potentially more ways. But one interesting way to do this was actually suggested in the domain of reversible neural networks. This idea has been applied successfully and involves basically not just doing solely integer multiplication or solely integer division, but it involves actually doing integer multiplication and division in a paired arithmetic operation. In other words, suppose I had some input variable x representing one of my velocity variables or one of my displacement variables. And in addition to that variable x, I also have some ancillary variable. I'll call it x star. And if, let's say, I wanted to multiply x by some integer a, at the same time as I carry out that multiplication, I also carry out the inverse operation on my ancillary variable x star. So rather than multiplying x by a, I divide x star by a. And at the same time, when I do that division operation, I also have some remainder that comes about from dividing that x star by a. But the modulo remainder that I get from that operation, which would otherwise be dissipated or lost permanently, I actually carry over and add to the result of my operation x times a. And in doing so, I actually don't really incur too much of an error in updating my value of x to obtain this new value, y, which is equal to x times a plus whatever remainder I had after division of x star. It turns out that that extra little remainder that I've tacked on to the end of x times a is really just kind of a little bit of noise. It doesn't really perturb the solution all that much. And in general, it doesn't really affect your solution significantly. So surprisingly, the nice thing about this operation is that it actually preserves that information just by taking whatever remainder I would have gotten from dividing x star by a and basically adding it into the result of the other variable, the one that I was multiplying, in other words. So all the information in this paired integer multiplication and division operation is perfectly preserved. So that's really our goal. And you'll notice that the architecture of this particular paired integer multiplication and division operation somewhat resembles the architecture of low-level logic gates in reversible computing systems, as were commonly applied in the context of quantum computing environments. To provide a little bit of context, quantum computing is really intensely interested in developing algorithms at all scales, all the way down to the logical scale and up even to the arithmetic scale. They'd like to come up with algorithms that are exactly reversible, and there's a few reasons for that. But the same kinds of concepts that can be applied in those domains actually apply in this domain as well. And usually the terminology they use is that these extra inputs that you have to add in order to ensure reversibility are sometimes called ancilla bits, and the output that you get that is not the main result that you were interested in is sometimes called garbage or garbage bits. But in our case, these extra garbage bits, they're not really garbage. In fact, the garbage is really the thing that we want to hold on to. It's essentially the information that we would otherwise throw away in our forward-in-time analysis, entailing all that information involving those residuals or those remainders that we were otherwise discarding. So in preserving that information, the garbage, we actually are able to recycle it, maybe as a better kind of terminology to use. It's not garbage, it's recycling. So that's the idea. It turns out you can also reverse these operations, and if you wanted to carry out integer division, the main operation that was not reversible in the case of integer arithmetic, just using these normal numbers, it turns out just by dividing x by a, I'd lose that remainder term, but if I use this paired integer division/multiplication operation, all I have to do is carry over the remainder from dividing x by a and add it to my garbage bits, or my recycling bits, if you like. Now, it turns out that this gate is really its own inverse. And you can obtain its inverse by permuting the inputs, or permuting, x and x star to obtain basically the paired multiplication division operation, or the reverse, the division multiplication operator. So it's a perfectly reversible operation. And if you do that, if you take one of these gates and then apply its permuted inverse, you get back the exact original values for x and x star. You can try it out, you can work it out on paper, you can prove it mathematically, but essentially it does exactly recover those original values for x and x star, but you do have to preserve what this extra state is, this x star term. So you have to double the number of solution variables that you're tracking at any one time that are being represented in this way. Okay. Now, of course, we're never actually multiplying by integers. We're always trying to multiply by usually some real number. But you can actually reasonably approximate a real number as a rational number, or in other words, as some numerator and a denominator, both represented as integers, and using these operations of multiplication and division in a pairwise sense, you can effectively carry out these multiplications by a real number approximated as a rational number by applying both of these operations in sequence, and that too is also by construction a reversible operation. So now we have a way of doing reversible multiplication of numbers using this whole kind of extended approach of a reversible paired integer multiplication and division operator. Now, the question is, moment of truth, does it actually work? It turns out it does, at least for this very simple problem involving mass proportional damping, in which we have really just these extra scalars that we're multiplying our primal variables, the velocities, by. But we don't just have the velocities anymore. We have to introduce this additional or ancillary velocity variable into our original solution. So not only are we updating the velocities in time, but we're also updating these ancillary velocities in time in the context of our paired multiplication and division operator. Now, if we do this, if we track all of that extra information in these ancillary velocity variables going forward in time, then when we reverse the operations going backwards in time, basically flipping the sign of these addition operators to become minus signs and flipping the order of this multiplication and division sign, that's really the only thing we have to change to go backwards. It turns out that we do exactly reconstruct the original solution from the forward in time problem. And we get back the exact original total energy, and we go back to the exact original configuration of the system. Kind of miraculous and kind of hard to believe that this even works. But you can try it out. You can definitely, I encourage you to do the exercise and play around with this in your own way. But it is possible to do this, which is kind of insane. So what are the implications of this? And also what are the other limitations of this whole approach? Well, consider some comparisons. How much does this really help us? And, is it really necessary? And, how much better does it improve upon just the simple fixed point arithmetic operations we were doing previously? The ones that didn't involve this paired integer multiplication and division operation. Well, even for problems that don't necessarily have a high degree of sensitivity to, small perturbations, like that triple pendulum problem, for sufficiently large problems and sufficiently long run times, you can still incur noise, numerical noise that creeps into the solution, and it really pollutes the solution if you go backwards in time. And part of the reason is, whenever you have a problem that has dissipation running forward in time, now when you reverse the flow of time, that system, which was originally dissipative and naturally stable, now becomes naturally unstable when you try to run it backwards in time. And that's a huge problem because in general, when you're doing computational and numerical methods, solving problems that are naturally unstable tends to lead to really crazy results. Results that in general are very sensitive to the inputs, or in this case, the end state of the simulation that you're trying to simulate. So the problem is those minor perturbations in the solution can effectively propagate to a high amount of noise that you wind up with once you rewind the solution all the way back to the beginning. You don't have that problem, however, if you use this paired and exactly reversible integer multiplication division operation. And that's really the advantage of this whole approach, is that you get around that issue of systems that were originally going to be unstable when you ran them backwards in time, now are carefully controlled. It's not that they are not unstable, however. They are still unstable systems when you run it backwards in time. It's just the case, however, that it's controlled chaos. Basically, you're carefully seeding the instability in this unstable system using that same error that you accumulated going forwards in time, which is being saved in these ancillary variables that you're carrying around. So you're still unstable, but you're unstable in a very controlled way and in a predictable way that gives you back the exact original forward in time solution trajectory. So that's the distinction, and that's really what's going on here. Also, what's the difference between fixed precision numbers and floating precision, or rather floating point numbers, at least from a computational efficiency standpoint? Well, it turns out if I'm using 32-bit integers to represent my solution in my fixed point implementation of this whole approach, that effectively I have to double the number of variables that I'm storing, because obviously I have not just my primals velocity variables I have to hang on to. I also need to hang on to the ancillary state variables, the ancillary velocities, and update them in time as well. But it turns out that doesn't really, increase my memory footprint, because a typical floating point number, at least, implemented in most, computational analysis tools, is represented as a double precision number or a double wide kind of value. So using 64 bits. So it's the same memory footprint. And in terms of the solution accuracy, you can kind of see that they're not exactly the same. There's a little bit of graininess to some of these, results that I'm getting using fixed precision numbers. The wave fronts here look a little bit sharper, as opposed to in the floating point case, they're a little bit more diffuse. But qualitatively, the solutions actually look pretty similar and do a fairly good job of capturing the overall essence of the simulation that I'm trying to analyze. And moreover, the overall computational runtime using floating point precision versus fixed point numbers is actually fairly comparable. It's maybe 6% slower for this problem involving, close to 250,000 degrees of freedom and, roughly 1,000 time steps, but that's actually pretty good. Overall, it's not a significant slowdown. Of course, this is on just using my, Macintosh laptop, so who's to say how this is going to scale on, GPU hardware, but that's a subject for future investigation. So we'll get there. Eventually, we'll get there. All right. Now, what can we do more with this? Is there other things that we can do with this new set of tools that we've developed for reversible integer addition and multiplication and all these different operations? Can we do more than just reversible integer addition and multiplication by a scalar number? More specifically, can we do reversible matrix multiplication and inversion operations? And it turns out that, it depends on how you carry it out. But supposing you had some matrix that you could decompose in an LDU kind of decomposition, where L is a lower unitriangular matrix, U is an upper unitriangular matrix, and D is a strictly diagonal matrix. If I approximate these entries of the diagonal matrix D by corresponding rational numbers, then it turns out that I can, in fact, perform a reversible set of operations to do integer multiplication, or rather, multiplication of this matrix A times some vector X. And to reverse that sequence of operations in a perfectly bit-reversible fashion, all I have to do is carry out this sequence of forward and backward substitutions and scaling by the diagonal elements of D, using all of my perfectly reversible integer arithmetic operations that I've developed, and using this paired integer multiplication division operation when I come to multiply by the diagonal matrix D, approximated by these rational numbers. So the inverse of this operation entails just flipping the sign of these operators. That's the only difference. It's kind of remarkable. And we can even go one step further, something even crazier. What if I had, let's say, some nonlinear constitutive behavior represented through this Bingham-Maxwell model as a prototypical example, a typical model of elastoviscoplasticity, in other words. It turns out that for such a model, you can pose it in terms of various different time integration schemes in order to update the internal solution state of this model, entailing this internal state variable for the plastic strain or the viscoplastic strain that I have to update every time step and at each integration point in my computational domain. Now, the forward in time update using a so-called exponential integrator turns out can be exactly reversed in time just by reversing the order of the operations that I carry out and reversing the sign of these operators that I'm applying. And it turns out doing that, I can actually apply exactly these same reversible multiplication division operators and addition operators, treating these internal state variables also using fixed precision numbers. And doing this, I can do some really crazy stuff, like in this simple uniaxial implementation of that elastoviscoplastic material model. On the right, I have my perfectly reversible, implementation of an elastoviscoplastic truss being subjected to this dynamic impact. And just for good measure, I'm also including some element deletion, and keeping track of the deletion time. I can also figure out when do I have to, activate or reactivate these elements when I traverse the simulation going backwards in time. So I have to keep around some extra details to figure out when I need to reactivate or birth these elements that died going forward in time. But otherwise, doing all these different things and applying exactly this bit-reversible approach, I can even reverse in time this crazy, nonlinear problem. And potentially use this in the context of solving inverse and optimization problems for these transient dynamic events that involve extreme material behavior and nonlinearity. In comparison, again, looking at the floating point simulation, trying to do the same thing, applying the same exact algorithms which ought to be reversible, but owing to the fact that we're using floating point arithmetic, and those floating point errors accumulate and grow in an unstable way, an unpredictable way going backwards in time, I certainly don't recover the original solution. And worse than that, it just blows up. It doesn't even work. So kind of remarkable that this whole concept can even hang together. But again, it's sort of an interesting idea that hopefully has a lot of future applications. And the intent is to explore this and apply this in the context of solving ever more complicated and interesting optimization and inverse problems, especially at larger scales, which are typically difficult to solve because of their high memory or computational requirements. So that's really the primary utility and the eventual application of these ideas. Now, there are certain limitations that are worth noting. Obviously, if you're using fixed point numbers, you have to deal with the issue of overflow. And overflow is never a problem in the case of floating point numbers, because usually you never really reach the maximum or minimum representable number in a floating point number system. But with fixed precision numbers, it's certainly possible that you might overrun or underflow the maximum or minimum representable number in that fixed point number system. So that's a problem. Certainly you have to be very careful when you're designing what the radices are that you're choosing for your problem, so that you ensure that you're always within those ranges. And otherwise, you have to figure out, if there is an overflow, what do I do about it? Do I need to extend my increase the size of the integers that I'm using to represent the mantissa dynamically at runtime, or do I need to do something else to fix that? And really the bigger problem is, what do I do with these ancillary variables which too can overflow? In fact, that's probably the greater challenge and the greater limitation of this whole methodology. If you have a lot of dissipation in your problem, then in general, my ancillary variables will be growing proportionally, inversely proportional to the rate at which my primary velocity variables are diminishing. So if I'm continuously decrementing the velocities in my problem, at the same time, I have to increase the size of my ancillary velocities. And if the rate at which the primal velocities are decreasing is relatively quick, then the ancillary velocities are going to grow exponentially, which means that you may have to continuously save that extra information that you would be getting in your ancillary variables, which would lead to an overflow. And there are ways, as I mentioned, that you can deal with that. You can either increase the size of those variables, but if it's growing very fast, then that requires a lot of extra memory. More commonly, you can just siphon off that extra information and save it in some kind of external context. That also entails some limitations. However, speculatively, if there's one way to do this where we're kind of saving all the information of these remainders, as we have from the method of Maclaurin that originally proposed this paired integer multiplication and division operation, it's effectively like we're doing some form of streaming bit compression on these extra ancillary remainders that we're siphoning off every time we do a division. So the question is there a more efficient bit compression technique that we could apply that makes it such that we can still preserve all the information, but in a slightly more compact way that doesn't require so much memory? So that's really the game that you have to play. And there's a lot of interesting investigations that will follow from it, maybe following that to its natural conclusion. We'll see. Maybe there's a way to do it. Maybe there's not. But in any case, it'll be interesting. Regardless, the other thing worth mentioning is that not all computational methods are obviously naturally reversible in time. I presented a few examples, these second-order dynamic systems, including even this first-order system like the elastoviscoplastic integrator for that simple uniaxial constitutive model. But not all systems are naturally reversible in that way, and not all operations are naturally reversible in general. So you have to be careful in the design of your methods if you intend to make them reversible. You have to be careful and ensure that they are inherently mathematically invertible operations that you're proposing to implement. Otherwise, it just doesn't work at all. You can't reverse something that doesn't have an inverse, and moreover, something that doesn't have a unique inverse. So ensuring that there is exactly a one-to-one mapping between simulation states, between adjacent time states in your overall simulation. If there isn't such a unique mapping, then effectively there's no hope that you'll ever be able to reverse those operations. So that's a critical limitation that's worth noting. And obviously that limits the scope of computational methods that you can apply this whole concept to. But nonetheless, as I demonstrated, there's still some interesting situations where, even if you have a lot of nonlinearity and even contact, frictionless contact in this case, and other things like that, you can still reverse it in time, which is pretty remarkable. And of course, the other issues are that in this whole approach, I should mention when I'm doing these computations, I really only need to use fixed precision arithmetic in the context of the time integrator. So when I'm doing the update of the velocities and the position variables in my simulation, that's when I need to do a reversible integer addition and subtraction and multiplication and division. But in the context of solving my finite element problem, if I'm assembling some collection of forces that are due to the deformation of some collection of finite elements that I'm using to discretize my problem, all of the computations that happen in that context that I use to come up with what are the current configurational forces of the system given the currently deformed state of that system, all of those computations can be carried out using conventional floating point arithmetic. That's really important because obviously that's really where I think most of the critical and highly sensitive computations are carried out, which ought to be done in floating point anyways. So thankfully, it's not like you're doing fixed precision arithmetic everywhere. And in fact, I really doubt there's even fixed precision implementations of certain mathematical operators. Things like sine and cosine and exponential and logarithm and all that stuff. You'd have to figure out how do you implement that and get it all working. Thankfully, that's not where you have to apply these concepts. It's really just the time integrator. And that's really cool because it basically means that I could just plug and play. If I have an existing finite element code, then really the only thing that I need to change to try to do this reversible implementation idea is I need to change the time integrator. But that's it. And assuming, however, that the form for my residual computations can be expressed in the format that I presented previously, such that the configurational forces of the system are really only dependent on the currently deformed state of that system, then it's amenable to that kind of reversible implementation. The limitation, however, is that you have to be consistent in the way that you compute those residual forces. And now, certainly the same errors that you would make using floating point arithmetic, you can make those again going backwards in time and everything. As long as you're consistent in how you evaluate the residual forces, then you're going to be okay. But if you have things like multi-threaded implementations of those computations that depend on the order in which certain operations are carried out, such as atomic reduction operations or other things like that, then you actually introduce the potential for those operations to result in non-deterministic results. And that slight non-determinism can actually lead to failure for the algorithm to become reversible. So you have to be perfectly consistent in how you carry out those operations and totally deterministic in order to ensure that you have perfect reversibility. Now, all of that being said, there's a lot of interesting investigations to follow as we continue to dive into this subject. More inelastic constitutive models and extensions to continuum viscoplasticity and fracture and other types of things, friction and all that. A lot of really interesting mechanics that if you can demonstrate that there's a way to do it in a reversible way, it would really open the door to solving a lot of other interesting problems in optimization and inverse problems generally, using this kind of bit reversible approach and in a way that accelerates the computation of sensitivities to solve those types of problems. Now, there's obviously a lot of work to do as well to demonstrate that this method is also performant and scalable on modern computing hardware, and I'm talking GPUs. So the advantage of using GPUs is that you can get the computations to run faster by, multi-threading them. But as I mentioned before, if there's some, issues with non-determinism in how those computations are carried out, then that's going to be a problem for bit reversibility. So you have to overcome that. And you also have to demonstrate that there's an advantage to doing this in running on the GPU. That somehow you overcome some limitations of the memory bandwidth limitations in communicating information to and from the GPU, which you would otherwise have a lot of if you were to do some kind of checkpointing scheme. Saving and loading data on a regular basis to and from the GPU might incur a lot of memory bandwidth overheads and latency, and that can slow down your overall simulation, such that it's the I/O that really kills your performance and your ability to accelerate the computation of these computations on the GPU. If you're trying to do an adjoint computation that's GPU accelerated. But if you're using a perfectly bit reversible computation, and if you're storing just the primal and ancillary state variables and storing it continuously on the GPU, then there's no I/O that you have to deal with, or very minimal I/O that you have to worry about in order to carry out everything just perfectly natively on the GPU. So that's the advantage. It's great if you can keep a minimal amount of energy or minimal amount of information and memory and keep it all on the GPU the whole time. And eventually we need to demonstrate that this actually helps us solve our optimization problems in general. So a lot of extra work that we have to do, a lot of interesting work to come, but stay tuned. This is really just a preview and the beginning of where we're going with this work. If you're interested, feel free to reach out to me. And if you have questions, I'm more than happy to entertain them. But otherwise, I thank you for your attention, and I really look forward to sharing more about bit reversible computational methods with you in the future. Stay tuned, and thank you.